Hello and welcome to second lecture in chapter 20, practical statistical analysis in Python. Now, in this, there are three parts. One part is implementing statistical calculations using SciPy and stats model. And in previous lecture, which was the very first lecture, we had just seen a few examples. And as I said in that lecture, that we will not be discussing these examples in detail because in subsequent chapters, many of these examples, in fact, 95% of these examples will have to be covered, without which data science cannot be progressed. So one is this thing, this we have already done, descriptive statistics. Hypothesis testing also was done. Then linear regression analysis, that we have not done, that we are just now doing in this lecture. Okay, OLS regression. Then robust standard errors, that we will do as the course progresses. Generalized linear model, that also we will do as the course progresses. Time series analysis, that we will do as the course progresses. Multivariate analysis as the course progresses. Non-parametric tests. Then survival analysis and model diagnostics. Then instrumental variables IV and two-stage least square, that is 2SLS, two-stage least square, quantile regression, maximum likelihood estimation, and Bayesian statistic, in which important thing is this Markov chain Monte Carlo simulations. Now, most of this will be covered in subsequent chapters, and some like this have already been covered. So, let us start with this thing, linear regression analysis, that is ordinary least square regression, right? Okay, so now as such, about this ordinary least square regression, we have done scattered discussion several times in previous lectures. But now in this lecture, we will do a systematic description of this technique. What is this technique used for? Then it is used for estimating relation between dependent variable and independent variables. What is the example of this? Then the example is what we have shown here. Suppose y is my dependent variable and x is my independent variable, and this is a scatter plot of various data points shown by black dots. I'm talking about the left side diagram at present, okay, and black colored dots, they are the data points. So the data is distributed in this manner, and it seems that there is some trend like this green line, okay, or in other words, it looks like y and x seem to be approximately linearly correlated. So what we do is we try to find what is the relation between y and x. Now here we make one such equation, y is equal to beta 0 plus beta 1 into x1. Now this is the standard equation that we know of straight line. Some books write y is equal to c plus mx, like that. But in short, the dependent variable is equal to some constant plus some other constant multiplied by independent variable, where we are taking at present a simple case in which there is only one dependent variable and there is only one independent variable, x1. Then we can complicate the matter further as required. But it is better to start with a simple case. So the data points are in xy plane, and this is the relationship between them. But at present I don't know what is this beta 0. And at present I don't know what is this beta 1. So estimating the values of these two constants will give me this kind of equation, right? That y is equal to 7 plus 5x. Now once this equation is obtained, then you can say that you have estimated the relationship between your independent variable x1 and your dependent variable y. Because now onwards, if anyone asks me that if x1 is equal to somewhere here at this point on this x-axis, further prolonging that x-axis, right? So if x is somewhere here, then what will be the corresponding value of y? Then I just have to plug in the value. So that is called estimating the relationship between independent variable and dependent variable. Okay, so that is called ordinary least square regression. Now, in this ordinary least square regression, what we do is we do not get this relationship mathematically. We do not even get it graphically, but graphically we have shown just for the understanding. So what we do is we think that this is some line of fit, green colored line, which is the closest possible line to all the data points. Now, as you prolong that line, it intersects this y-axis here. Then this much, what is shown by red color, that is the intercept on y-axis. And similarly, I can find the slope of that line with respect to x-axis. What angle does it make? Say theta is the angle made with respect to x-axis, and then tan theta will be called the slope. Okay. But those intercept and slope are the constants in which you are interested. Now, as you try to estimate them, the important thing is to get the line of best fit, because there can be several such lines. In fact, infinite number of lines. One person may say my green line is my line of best fit. Other person may say that no, this red line is my line of best fit. One another person may say that maybe other color, this orange line is my line of best fit. Orange and this dotted line, that is the line of best fit, like that. The question is who is correct. Then for that, now I'm removing the other lines. I'm keeping only green. Suppose the green is the actual line of best fit. Then how do I know that green is the actual line of best fit? For that, I have to take for each data point one by one the actual value of the data point, which is the vertical height of the black dot, and the predicted value of the data point, that is this. Okay. So on the line, and I have to find the difference between them, which is shown by this orange color cursive bracket, right? So that shows that this is called y actual, or just simply called y, and this is called here on the axis, this is called y predicted, that is called y predicted, and it is often shown by y hat. Then what we do is we find the difference between the two, y hat predicted value minus actual value. So here in this case my predicted value is high, that is itself predicted value, that is less, while the actual value is high, actual value is more. So that means that this particular thing is the difference between the two, actual and predicted, or that means this is error or absolute error, right? Now once this absolute error is found, suppose it is shown by epsilon 1, that is absolute error in observation 1. Now here this would be negative because my predicted value is smaller. So I do one thing, I square it, so that negative value becomes positive. So then that is epsilon 1, or rather suppose the previous one was root epsilon 1, so that I will call now the squared value itself the error, squared error in the first observation. Similarly, I take second observation, these observation, and again I can find actual value minus predicted value. But for this time, I take some observation below. So in this case, suppose I take this observation, okay, this one. So what is the actual value? That is shown by that dot. So that is y actual. And what is the predicted value? So that is y predicted, which is will be on the green colored line, which is drawn vertically from passing through that point. So these would become the y predicted value, right? This. So height of that point. So that you can see this time predicted value is higher. So that means if I do y predicted minus y actual, because this is slightly wrong, I have done actually actual minus predicted. Yeah. So then suppose if I do y predicted minus y actual, because here also we have done predicted minus actual, then this time the answer would be positive because my predicted value is this point, and my actual value is this point. So that is why y predicted minus y actual is positive. But again I square it and so on. So this is suppose, and that squared value that gives me error term in the second observation. So that is, this is called squared error in the first observation, squared error in the second observation. Now what I have to do is I have to take all the observations starting from 0 to n, where n is the number of observation, and I have to find squared error in each, and I have to do summation of them. So that mathematically will be shown like this, that sigma y predicted minus y actual whole square for I equals 1 to n, where n is the number of data points in my sample. This quantity is called sum of squared error. Name itself is indicator. Sigma means sum, and this bracket is squared error. So sum of squared error. Now the line of best fit is such a line which makes this sum of squared error minimum. So the error terms must be minimum. So as I said, there can be several lines. One person may show that I want to draw red line, and another may show that I want to draw the blue line and all that. The question is whose line is the line of best fit? And I said that green is the line of best fit. Now the question is why? Then the answer is that it is because the sum of squared error for that green line is minimum. Or in other words, in common language, I can say that the green line is the closest possible line to all the data points, right? So then sum of squared error is minimum, or this is the line of best fit. Now the question is, can I find a line which is passing exactly through each and every point? Now that is clearly not possible, that we can see, because unless and until the data points themselves are on one line, which is always very rare or hardly in any practical data set, you will get that kind of thing. But if the data points themselves are like this on this line, okay, and say this is one data point, so this is one data point, this is other data point, this is other data point, this is yet another data point. So actually line I am showing below just because the drawing with mouse is a little bit difficult, but that this line is passing through all the data points like this. And in that case, the line of best fit will be a linear graph, and in that case, the error term would become 0. But that is nearly impossible thing. because there cannot be that kind of linear distribution, perfectly linear distribution, unless it is a synthetic data. So in this case, what you have to do is you have to be satisfied with some error and you have to try to minimize that error. Okay, so that is what we have done. So in short, whenever you write that equation, y equals, that is your dependent variable equals some constant beta 0 plus some other constant beta 1 multiplied by x1, this, right? And then you have to add one term, that is term is called epsilon. This is itself the total sum of squared error in entire experiment, that is SSE, right? So this is the total sum of squared error in this experiment of finding the line of best fit for this data distribution. Now there are a few things more also. We have seen that there is no need, or that there will always be only one independent variable. It might be possible that there are two independent variables, so that your equation would become somewhat like this: beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon. So that means this is called my total sum of squared error. Total sum of squared error, right? And at that moment, this is now a two-dimensional case. So at that moment, there will not be a line of best fit, but there will be a plane of best fit. So on this axis, that is on this axis, there is y. On this axis, there is x1, first independent variable, and on this axis, there is x2, second independent variable, correct? And these data points, they are spread in the plane made by x1 axis, x2 axis, and this y axis. So these are those blue colored dots, they are the data points, correct? And this gray colored plane, that is called plane of best fit. Just like this green is the line of best fit, similarly this gray is the plane of best fit. That is the plane which is the closest possible to all these blue colored data points. Okay, but the concept of linear regression will still hold. So ordinary least square regression will still hold, and it is still, the logic is same, that you have to find such a plane for which the sum of squared errors is minimum. Now unfortunately, at this case where two variables are there, two independent variables are there, our visualization capacity limit is over now. But in the data science, you will even have to handle 10 variable case and one dependent variable, or 10 independent variable, x1, x2 up to maybe x10. So it cannot be possible to do that in this manner, right? So what we do at that time, that we know that we do it statistically by ready-made functions which are available to us. That process is itself called ordinary least square regression. The word itself is clear, least square. This is the square and we are trying to minimize this. Least means the minimum. So a regression in which the sum of squared error is minimum. Now then, this one important application of this implementing statistical calculation in SciPy and STATS model, one important example is to provide diagnostic, that is R squared, p-value, confidence interval, and residual plots. Because when we obtain statistically such line of best fit or plane of best fit, then obviously there is error. So the question is if there is acceptable error or unacceptable error. How much error is there? What is the quality of fit of this line or this plane? Then the answer to that is given by this kind of statistics: R squared, p-value, confidence interval, and residual plots. So we want to talk a little bit about these things. Okay. So let us start with our data in this particular example. Now here I will be stopping this lecture. I gave an intuitive idea about ordinary least square regression. Actually, it should not have been required because we have discussed the same thing again and again. But still, now in next lecture, we will actually try to simulate the whole process by program, because we will, whenever we in data science will do this, and we will neither do by mathematics or nor do by this kind of diagrams, graphs. We will have to do it by programmatically. So we will take that example in our next lecture. Thank you and see you.